Now that we've talked about strong acids and strong bases and determined the pH of those solutions, we need to look at weak acids. We'll get to weak bases in the next section, but for now, we will look at weak acids. Weak acids are acids that don't dissociate 100%. They dissociate somewhat less than 100%. Here is a generic example, a weak acid HA. A could be any number of things, but this weak acid, when we put it into water, it dissociates and gives us hydronium ion and the conjugate base of our acid. We can write the equilibrium constant expression for this. We will call it Ka because A for acid, so we'll call it Ka, hydronium times the concentration of the conjugate base, and divided by the concentration of our weak acid. You'll notice that the water is not in the expression because water is the solvent. Ka is our acid dissociation constant, and so the first thing that we want to do is practice writing this out as an equilibrium reaction and an equilibrium expression. So we're going to look at number 51 in chapter 16. So here we've got number 51, and we want to write this out as an equilibrium reaction. You'll notice here it asks us to write it two ways, so I will write it two ways. We'll have the hydrogen ion as the product and one where the hydronium ion is the product. For the hydrogen ion as the product, we'll do HC6H5OAQ, and we will dissociate it to give us hydrogen ion AQ plus C6H5O minus AQ. And then I'll write it where we have it with water and get the hydronium ion, so HC6H5OAQ. And I left the water out. Let me fix that real quick. So plus H2O liquid, and that is in equilibrium with hydronium ion plus C6H5O minus AQ. Okay, so with this, we can write the equilibrium constant expression, Ka. Ka is equal to the concentration of hydronium times the concentration of C6H5O minus divided by the concentration of HC6H5O. Okay. The other way we could write that is with the second equation. We can put hydronium times C6H5O minus and divided by HC6H5O. And both of those, they represent exactly the same thing, and so there is no need to distinguish between them. As I mentioned earlier, I generally like to write it with the water in the expression because if you've got the H plus and it says AQ, then that means it is in the form of hydronium ion. So let's do the same thing for this one. And for this one, let's see, I'm going to see if I can write it right here. So AQ, and it dissociates to give us H plus CO3 2 minus AQ. Again, the other way that we can write that would be with water, so HCO3 minus plus H2O liquid, and that is in equilibrium with hydronium ion plus CO3 2 minus AQ. And we can write the equilibrium constant expression, Ka, is equal to the concentration of H plus times the concentration of CO3 2 minus divided by the concentration of HCO3 minus. Or we can write it with the hydronium ion, so H3O plus times the concentration of carbonate divided by the concentration of bicarbonate. And as I mentioned, both of those are legit and correct ways to write this. All right, so now that we've done these equilibrium constant expressions, we want to go back to our presentation and look at the kind of math problems that we are going to be doing with weak acids. So first of all, let's talk about what the value of Ka means. The greater the value of Ka, the stronger the acid. So here we've got a variety of different weak acids, HF, so hydrofluoric, nitrous, acetic, this one, what is hypochlorous acid, hydrocyanic acid, and phenol. That's actually the one we just looked at. And you'll see there is a range of Ka values. The bigger the value of Ka, the stronger that is as an acid. The smaller the value, the weaker it is as an acid. So those are just a couple of examples of some of these. We have a much more complete list, and we can see that complete list in Appendix D1 of the textbook. And so I am going to bring that up. Here is Appendix D1 in the textbook, and it's got the Ka values for a whole bunch of different acids. So we're going to refer to this multiple times in this chapter and in the next chapter. It is something that is very useful to understand how to use. Now, let's look at the type of math problems that we're going to have when we're doing weak acid problems. So there are different things that we might want to solve for. Here we've got the equilibrium reaction, the same one that I showed you on a couple of slides ago. So just our generic weak acid plus water gives us hydronium and the conjugate base. Well, and then here is the equilibrium constant expression, Ka. We might be interested in solving for the original concentration of our weak acid. That is a type of problem, and we're going to do one of those problems here in just a little bit. We also might be interested in solving for the value of Ka. So sometimes we want to know what that equilibrium constant expression or the equilibrium constant value is going to be. Since we have a big table full of them, that's not often what we're going to be doing, but that is occasionally what we will be interested in. We also might be interested in solving for the concentrations of either one or more of our reactants or products, or also the pH. If we know hydronium, we can get the pH at equilibrium. So equilibrium type calculations. And then finally, sometimes we are interested in calculating the percent ionization. And the way that we do that is that we'll look at how much hydronium ion there is divided by the concentration of the weak acid initially and multiply by 100. I'll show you an example of that coming up shortly. So first, here we've got a problem where we want to calculate Ka from pH and concentration. So here we've got a weak acid, formic acid. Just in case you're curious, formic acid, that is the acid that is in an ant bite. So if you get an ant, not a fire ant, they're different and evil. I'm talking about just a regular, good old-fashioned red ant. If you get bit by one, that pain that you feel comes about because of the formic acid. All right, so here we've got a 0.10 molar solution of formic acid, 25 degrees Celsius. All of our calculations are going to be at 25 degrees Celsius. This is just verifying that that is true. pH of 2.38. Calculate Ka. Well, if we're trying to calculate Ka, that means that we need the concentrations of all of the components in the expression at equilibrium. Well, here is the equilibrium reaction, and here is the equilibrium constant expression. All right, we need to calculate the concentration of hydronium, the concentration of the conjugate base of formic acid, which is formate, and the concentration of formic acid, all at equilibrium. And when we calculate those values at equilibrium, we'll put them into this expression and we can calculate what Ka is. So we use an ice table, a concentration table, to keep track. Here is our chemical equation again. And just to kind of give you an idea, our initial concentration of the formic acid is 0.10. Water we're going to be able to ignore. And then the initial concentrations of hydronium ion and the formate ion are going to be 0. So here is our concentration table. We've got the initial concentration of 0.1 for our formic acid. Water we ignore because water is not in the expression. Hydronium ion is 0, and the formate ion is also 0. We will find here in Chapter 16 all of our concentration tables, all of our ice tables, are going to have 0 in the initial, on the initial row over on the right side of the equation. When we get to Chapter 17, the whole point of that chapter is going to be looking at what happens when one of these is not 0. And that'll be an interesting thing to do. The change line we're going to put in terms of x. So this one decreases by x and these increase by x. Just as a reminder, the coefficient of x must be the same as the coefficient of the chemical in the balanced equation. Since these are all 1, that's why these are all 1x. So 0.10 minus x gives us 0.10 minus x, and then 0 plus x is x, 0 plus x is x. So now we'll put those values in terms of x into this expression. Well, this is x times x, so that's going to be x squared up in the numerator, and down in the denominator we will have 0.10 minus x, and that will be there. Well, to get x, we can get that from the pH. We know that the pH was 2.38, and we can calculate the hydronium ion concentration at equilibrium using 10 to the negative pH. So hydronium is 10 to the negative pH. So 10 to the negative 2.38, that comes out to 4.2 times 10 to the negative 3. That means we can take 4.2 times 10 to the negative 3 and put it in for x in this expression. When we do that, 4.2 times 10 to the negative 3 squared over 0.10 minus 4.2 times 10 to the negative 3. That equals 1.8 times 10 to the negative 4. So now we have calculated Ka for this acid. If you go and look at Appendix D1, which I'm going to do real quick, and we look up formic acid, we'll see that it is indeed 1.8 times 10 to the negative 4. All right, so now we have done that. Now there's one more thing that I want to do before we move on to the in-class assignment problem. And that one more thing that I want to do is calculate the percent ionization. When it comes to calculating percent ionization, we will do the concentration of hydronium ion at equilibrium divided by the concentration of our weak acid initially. Now, one point I want to make about this is if you want to generalize this so that we don't just do it with a weak acid, like a little bit later we're going to be talking about a base. Really what we're doing is we're saying what was the concentration of whatever it is we were talking about initially, and how much did it change? And we're going to take the amount that it changed divided by the initial amount. And that's really what the whole point of this calculation is. Multiply it by 100 to make it a percentage. When we put the numbers in, the equilibrium concentration of hydronium was 4.2 times 10 to the negative 3. Our initial concentration of the formic acid was 0.10. And when we put that into our formula, we'll get 4.2 times 10 to the negative 3 divided by 0.10 times 100, and we get 4.2%. That 4.2% indicates that 4.2% of our formic acid molecules are dissociated at any given time. Okay, so let's look at number 57 on the in-class assignment. So here is number 57. In number 57, we have a sample of vinegar. It has a pH of 2.90, assuming that the acetic acid is the only acid in the vinegar, and that's the case like in most vinegar. Ka of that 1.8 times 10 to the negative 5. Calculate the concentration of acetic acid in the vinegar. So this is one of the kinds of problems where we're trying to determine what the initial concentration of our acid is. Now, it says acetic acid, and I know the formula for acetic acid, but to save a little bit of space, I am just going to write this as HA instead of writing out the full formula for acetic acid. We are going to be doing a concentration table directly beneath, so I'm going to put ICE directly beneath. And so HA plus H2O liquid, and that is in equilibrium with hydronium ion plus A minus, AQ. Okay, so we need to put in a variable for HA. For water, I'm just going to put a line there to indicate that we don't need to write values for the water. Water is the solvent, and so we don't need to worry about that. But for HA, we need a variable. I don't want to use the letter X, and the reason I don't want to use the letter X is because I like to use the letter X for something else. So I like to use it for the change line. So for the original concentration of the weak acid, I am going to use the letter C. For the initial concentration of hydronium and the conjugate base, acetate, I'm going to put 0. As a reminder that will be the case for all of our problems here in Chapter 16. For the change line, this is where I like to use the variable X. So here it decreases by the amount X. This will increase by X, and this will also increase by X. So for our equilibrium values, we'll have C minus X, X, and X. For our equilibrium constant expression, Ka, that is equal to the concentration of hydronium ion times the concentration of our conjugate base. divided by the concentration of HA. All right, we know from this that our concentration, that our equilibrium constant expression, our equilibrium constant value here is 1.8 times 10 to the negative 5. So Ka is equal to that. So we're going to take these values in terms of C and X and put them into this expression. And for Ka, I will write 1.8 times 10 to the negative 5, and that's equal to X squared divided by C minus X. All right. We need to calculate the value of C. But in order to do that, we need to get a value for X. Fortunately, we can do that relatively straightforward. X is equal to the concentration of hydronium ion at equilibrium, and since we have the pH, that means that we can calculate the concentration of hydronium ion at equilibrium. So X, which is equal to the concentration of hydronium ion at equilibrium, is equal to 10 to the negative pH. That means our hydronium ion, which is also equal to X, is equal to 10 to the negative 2.90. So 2.90. Well, now we'll get out our trusty calculator and calculate the value of the hydronium ion, which is also X. So we will do 10 caret negative 2.90 and give us this value. You'll see that it says 0.00125889. Technically, we've got 2 sig figs, but I'm going to go ahead and write 3 sig figs, and I'll explain why that's the case here in just a moment. But X, which is equal to hydronium, which is equal to 1.26 times 10 to the negative 3 molar. And that is the quantity that we are going to use to solve the rest of this. So now we've got 1.8 times 10 to the negative 5 is equal to 1.26 times 10 to the negative 3 squared. We do want that square there. Divided by C minus 1.26 times 10 to the negative 3. And we just want to solve this equation for C. First thing, I'm going to multiply both sides by C minus 1.26 times 10 to the negative 3 and divide both sides by 1.8 times 10 to the negative 5. So when we do that, essentially we're switching places between these two values, the value here and the value in the denominator. So that will give us C minus 1.26 times 10 to the negative 3 is equal to 1.26 times 10 to the negative 3 squared over 1.8 times 10 to the negative 5. And now we're going to add 1.26 times 10 to the negative 3 to both sides of the equation. So C is equal to 1.26 times 10 to the negative 3 squared over 1.8 times 10 to the negative 5 plus, because we're adding it, so plus 1.26 times 10 to the negative 3. Now, let's use our calculator. So 1.26 times 10 to the negative 3 squared divided by 1.8 times 10 to the negative 5. And that gives us this part. And now we're going to add to that 1.26 times 10 to the negative 3. 1.26 second EE negative 3. All right, and in doing that, you will see that we will get our answer. And that answer comes out to 0.08946. We're going to round that to 2 sig figs, so we're going to call our concentration C as 0.089 molar. And that is the initial concentration of our acid. Now, I'm going to make a quick comment here about this number. So this number. Here I didn't round this to 2 sig figs as I probably should have. I just left it as 1.26 times 10 to the negative 3. I went through and did this calculation using 1.3 times 10 to the negative 3. And when I did that, the initial value that I got for HA was actually 0.095. So we do get a fairly significant difference in that value if we round than versus if we don't round. That just goes to show you that sometimes it's worth it to take a look at that and see what happens when you round versus not rounding. So now we're going to go back and look at the in-class, or look at the lecture. And we're going to do another type of calculation. And this type of calculation is the one that you're going to need to spend a little bit of extra time practicing. Sometimes people find it challenging, but once you get the hang of it, you're going to get good at it. So calculating pH and percent ionization when you know Ka. So here, the question is, calculate pH and the percent ionization of a 0.30 molar solution of acetic acid at 25 degrees Celsius, and here is the Ka value. If you get a problem like this and it doesn't tell you what Ka is, you'll need to go look it up in the appendix. But here we're trying to determine pH, and we have an initial concentration. That tells us right away that we have a concentration table type problem. When you're doing this, the best thing to do is to write out the chemical equation first for the dissociation of the weak acid. So here I've got the acetic acid, so HC2H3O2, plus water gives us hydronium, and the conjugate base, our conjugate base is C2H3O2 minus. Here is our concentration table. Our original concentration was 0.30. Just like we saw in the previous couple of problems, the initial concentration of hydronium and the acetate ion are 0. As I said throughout chapter 16, that's going to be the case. This one will decrease by x, so 0.30 minus x, and these two will each increase by x, giving us x and x. Our equilibrium constant expression is going to be hydronium times acetate over acetic acid. And so there is our expression. We were given in the problem the value of the equilibrium constant, Ka. So there is the Ka, 1.8 times 10 to the negative 5. And then we want to put into the expression the values in terms of x. So here we've got x squared over 0.30 minus x. And that is our Ka value. Well, this is a quadratic equation. In quadratic equations, we will find that there are two approaches we can use to solving these quadratic equations. One, we can use the quadratic formula, and I'm going to show you how to do that on the next page. So, solve the quadratic equation using a quadratic formula. Well, to use the quadratic formula, we need to get the equation into the correct form. And what that means is cross-multiplying this equation and solving for 0. So when we cross-multiply, so this times this, all right, so now we've got that times that difference. We are going to distribute this, so 1.8 times 10 to the negative 5 times 0.30 comes out to 5.4 times 10 to the negative 6. And then 1.8 times 10 to the negative 5 times negative x, so minus 1.8 times 10 to the negative 5x, and that's still equal to x squared. Well, now we simply want to move these two things over to the other side of the equation so that we will have 0 equals to x squared and then the rest of our normal form. So 0 is equal to x squared plus 1.8 times 10 to the negative 5x minus 5.4 times 10 to the negative 6. Well, this is where the quadratic formula comes in. The coefficients, when it's in this form, the coefficients of x squared is going to be a, the coefficient of x is going to be b, and this value is going to be c. Here is our quadratic formula. So x is equal to negative b plus or minus the square root of b squared minus 4ac. And then all of that over to a. Well, I think it's useful when you break out your quadratic formula. I think it is useful to pay attention to what the values are. A is really easy because a is equal to 1. B is a little bit more or slightly more challenging, but not too bad. It's just 1.8 times 10 to the negative 5. This is where people will commonly make a mistake. Remember, the generic form of this is ax squared plus bx plus c. Since this is a negative here, the value of c is negative 5.4 times 10 to the negative 6. If by accident you put positive 5.4 times 10 to the negative 6, you're going to get a negative value underneath that square root sign. Well, a negative value under the square root gives you an imaginary number, which gives us a complex number. I am here to tell you that we do not have imaginary values for concentrations. They all have to be real numbers. So we're going to take these numbers and put them into the expression. Remember, the plus or minus means that there are two solutions when we have quadratic equations, usually two solutions, and this is not an exception. So I had to shrink down the type. Sorry if that's a little bit difficult to see here. So negative b plus or minus b squared minus 4ac all over 2a. Since there's a plus or minus, we are going to get two answers, one where we use the plus sign and one where we use the negative sign. And so our values for x are going to be either 2.3 times 10 to the negative 3 or the negative 4.7 times 10 to the negative 3. And I mean, if this is just a pure math problem, these are both solutions. However, for chemistry, because x is a concentration, it has to be a positive value. That means that we can get rid of this negative value because we do not have negative concentrations. So x is 2.3 times 10 to the negative 3, and that is also equal to the hydronium ion concentration. If you go back and look at the table, you'll see that hydronium equals x at equilibrium. So that is equal to the hydronium ion concentration. Well, now we're just two quick steps away from getting the pH. So pH is negative log of 2.3 times 10 to the negative 3, and the pH is equal to 2.64. One last little detail here. It did ask us to solve for percent ionization. So percent ionization is the value of x, which is 2.3 times 10 to the negative 3, divided by our original concentration of the acid, which in this case was 0.30, and then multiplied by 100 to make it a percentage. And then here we get 0.77%. So 0.77%. Now, Using the quadratic formula is perfectly fine. You just need to be meticulous about it to make sure that you don't make any mistakes. However, we have a shortcut. And chemists, we always love to have shortcuts and ways to solve things that are a little bit easier. So I'm going to show you the shortcut. Our quadratic equation shortcut is this. We know that X is small. This is a weak acid. X is the amount that it dissociates, and so we know that X is a small value. Well, our shortcut is to say that X is such a small value that it doesn't really change this quantity. So this is 0.30, and it doesn't change very much. Because X is small, we can neglect it, and that is our shortcut. Now, when is it okay to neglect X? Well, if X is less than 5% of the thing that we're subtracting it from, then it's okay to neglect X. You can never neglect the X's that are by themselves. So if you neglect this X, then what are you even solving for? You can't do that. You can neglect if you're adding it to a number that's much bigger than the X, or if you're subtracting it from a number that is much bigger than the X. So we're neglecting X. Now, we already know that X was 0.77% of 0.30 because we did the calculation already. But if you don't know ahead of time that it's less than 5%, in this case it was even less than 1%, then how do you know it's okay to neglect X? Well, there's a trick. So for our shortcut, we have a trick, and the trick is to take this number, which is the initial concentration, and divide by the Ka value. If this number divided by that number is greater than 400, it's okay to neglect X. I'm going to go over to our calculator real quick, and we're going to put those numbers in. So we'll do 0.3, oh, I'm going to turn that on. So 0.3 divided by 1.8 times 10 to the negative 5. And if this number is greater than 400, it is perfectly okay to neglect X. Well, you'll see here that that number is 16,666, so almost 17,000. Well, that's definitely bigger than 400. If the number had been exactly 400, we would find that X would be equal to 5% of the thing we're subtracting it from. If this number comes out to less than 400, that means that X is not that small compared to the thing that we're subtracting it from. And so we'll have to be cautious. We can't really do it then. So here we come back, we've neglected X. So now this is 1.8 times 10 to the negative 5 equals X squared over 0.30. Well, at that point we just cross multiply that out, and take the square root. You'll notice we got the same number, 2.3 times 10 to the negative 3. If you leave a few more digits in there, you will see that the number we get here is ever so slightly different than the number we got on the previous page, but you're still going to get the correct answer when we consider the number of sig figs. So 2.3 times 10 to the negative 3. And this part is all the same since X is equal to hydronium. Then that gives us pH, and we can also solve for percent ionization. It's a good idea if you've neglected X to do the percent ionization to make sure that it really was okay to neglect X. Let's look at number 60 on the in-class assignment, and after we do number 60, that will be the end of this section, and we will be able we actually have one little more thing about polyprotic acids, but we're almost done with this section. So let's go over to the in-class assignment and do number 60. So for number 60, we've got this problem. The acid dissociation constant for hypochlorous acid is this, 3.0 times 10 to the negative 8. We want to calculate the concentrations at equilibrium for all of the things. If the initial concentration is 0.0075. Also calculate the pH at equilibrium. That'll be easy once we get hydronium. And the percent ionization, that will also be an easy calculation to do. So first things first, write out the equilibrium reaction. So HClO, AQ, plus water, liquid, is in equilibrium with hydronium ion, AQ, plus ClO minus, AQ. All right, I'm going to save this space for doing some other calculations here in just a few minutes. So we are going to do a concentration table, ICE. So we're going to do a concentration table. Our initial concentration of the weak acid was 0.0075. Water, we can ignore, so I'm just going to put a line there. Hydronium and the hypochlorite ion, initially, we're going to have 0 for those. The amount that it changes, well, the amount that it changed, this one's going to go down by x, so it'll be minus x, so 0.0075 minus x, and that this will be plus x and plus x. Our equilibrium constant expression, Ka, is equal to the concentration of hydronium ion times the concentration of the hypochlorite ion divided by the concentration of hypochlorous acid. So Ka, we know, is 3.0 times 10 to the negative 8. So now we'll write 3.0 times 10 to the negative 8 is equal to x squared over 0.0075 minus x. And here again, we've got a formula that, or we've got an equation where we could use the quadratic formula. But we also have the possibility that we could do the shortcut. And the shortcut is, can we neglect x? Our trick for that is to take this number, the 0.0075, which was our original concentration of the acid, and divide by the equilibrium constant, Ka, 3.0 times 10 to the negative 8. If this divided by this is greater than 400, which I can tell that it's going to be, then that means that it's okay to neglect x. But let's go ahead and punch that in the calculator anyway. So 0.0075 divided by 3.0 times 10 to the negative 8. And that gives us 250,000, and I think everybody can agree that is bigger. That is bigger than 400, so it is okay to neglect x. So I'm going to get my red pen of neglect and neglect x. Well, now that we've neglected x, this is what our formula looks like. 3.0 times 10 to the negative 8 is equal to x squared over 0.0075. So 0075. Well, this is an easy problem to solve. We're going to cross multiply that, and when we cross multiply that, we will get x squared is 0.0075 times 3.0 times 10 to the negative 8. Okay, so we'll do 0.0075 times 3.0 times 10 to the negative 8. All right, so 3.0 times 10 to the negative 8. Making sure I entered that in correctly. I did. And we get 2.25 times 10 to the negative 10, so x squared is 2.25 times 10 to the negative 10. And now we're going to take the square root of that. And so square root of our answer. And that's going to come out to X is equal to 1.5 times 10 to the negative 5 molar. Okay, so let's go back and look at what was the problem asking for. And what the problem was asking for is, what is the initial concentration of hydronium, hypochlorite, the equilibrium concentrations of hydronium, hypochlorite, hypochlorous acid, and the pH and the percent ionization. So we're almost done. We are almost done. This is our value of X. That is equal to the concentration of hydronium. We'll see here, it's equal to that. And it's also equal to the concentration of hypochlorite ion. So we've solved this and this. To get this, that's pretty easy. Our concentration of HClO is equal to 0.0075 minus X, and X is 1.5 times 10 to the negative 5. All right, so 1.5 times 10 to the negative 5. So 0.0075 minus 1.5 times 10 to the negative 5, and you'll see that we get 0.007485. Well, when we round that to the proper number of significant figures, we get 0.0075 molar. So really, the concentration of our weak acid doesn't change very much because so little of this actually dissociates. Okay, we need to do pH calculation now. So pH is equal to the negative log of 1.5 times 10 to the negative 5. So 1.5 times 10 to the negative 5. So we'll do negative log of 1.5 times 10 to the negative 5. Make sure I entered all that in correctly. I did. We'll hit enter, and you'll see we get 4.82. So 4.82 for our pH. Our final bit of calculation here is the percent ionization. So our percent ionization, not 8% is what I wanted there. So our percent ionization is going to be equal to, it's basically X divided by the concentration of our weak acid initially times 100. So in this case, X is 1.5 times 10 to the negative 5. We have 0.0075 and then times 100 to make it a percent. So 1.5 times 10 to the negative 5. We'll divide that by 0.0075. All right, and that's 0.002, and then now we multiply by 100, and that gives us 0.2. So 0.20% ionization. So you could see that is a very small number. All right, so that is for weak acids. I do want to go back to one more thing before we get to weak bases, and that is to look at polyprotic acids. So polyprotic acids are, these are acids that have more than one acidic hydrogen. Examples of polyprotic acid here, we've got ascorbic acid, carbonic acid. There's a whole bunch of these that are out there, and they have more than one hydrogen that is acidic, and with that, that means we get more than one Ka value. We will find always that the first Ka is bigger than the second. And that's because once you've removed one hydrogen from an acid, you now have something with a negative charge. That's going to make it more difficult to remove a second H+. So we will always find that Ka2 will be a smaller value. In other words, it will be more difficult to deprotonate, or it'll be more difficult to dissociate the Ka2 than it will be for the first hydrogen. If we're just doing calculations of pH, then often we're not concerned with Ka2 or Ka3. However, if we're looking at other things, like let's say we're not starting with that acid, let's say we're starting with bicarbonate, then in that case we're definitely going to be interested in Ka2 and Ka3. You will see that on table D1 that we've got Ka2 and Ka3 for different acids here, and so I will refer back to those a little bit later. So just one example of a polyprotic acid, we're going to pick carbonic acid. Carbonic acid is the acid that you get when you dissolve carbon dioxide in water. Well, carbonic acid has two dissociation constants. So here is the dissociation of carbonic acid to give us hydronium and bicarbonate ion. And that has a Ka value, Ka1, hydronium times bicarbonate over carbonic acid, and that has a value of 4.3 times 10 to the negative 7. For the second dissociation, well, some of that bicarbonate can dissociate in water to give us hydronium plus carbonate ion. And we can write the value for that dissociation constant as well. You'll see here that it's different by 4 orders of magnitude. So if you just have carbonic acid, there's almost none of the carbonate going to be present. I mean, there's going to be a small amount of bicarbonate present, but hardly any of the carbonate present. And that's what that tells you. However, and I mentioned this before and I'll mention it again, is that sometimes we're still interested in this value, and I'll show you what cases that's going to be true in a little bit. All right, so that's it for polyprotic acids, and I believe the next thing here is for bases. Yes, for weak bases. I'm going to make the weak bases part of the next video, so we are going to stop this video here.